All right, let's dive in. Today, we're going to talk about something that's literally all around us, but completely invisible, a world of silent, powerful forces that shape everything from our tech to our own bodies. We are talking about electric fields.
But here's the thing, right? The biggest challenge is they're invisible. So how in the world do you start to understand them? I mean, how do you even begin to draw a force that you can't see?
Well, the answer is pretty cool. We watch what they do to the things we can see. So what you're looking at right here are tiny little grass seeds floating in oil. But when you flip on an electric field, they instantly snap into this incredible pattern, perfectly tracing the invisible lines of force that are all around them.
You know, this whole idea of making invisible forces visible, we really have to thank the brilliant scientist Michael Faraday. He came up with a truly elegant way for us to actually draw a map of these fields.
He originally called them lines of force, but today we know them as electric field lines. And really, you should just think of them as a map of the invisible force. Each line shows you the exact direction of the field's push or pull. And if the line curves, no problem. The direction of the force at any spot is just the direction the curve is pointing at that exact moment.
A really great way to think about this is to picture streamlines in a river. You don't see the water itself, right? But those lines show you exactly how the current is flowing at every single point. It's the same idea. Okay, so we've got this map. Awesome. But any map is pretty useless if you don't know how to read the symbols. The good news is there are just a few simple rules, and once you get them, you can read any electric field out there. All right, so here are the rules of the road. Rule 1, field lines always start on positive charges and point away. Rule 2, they always point toward negative charges, and that's where they end. Rule 3, and this is a big one, they can never, ever cross. I mean, think about it, right? If they crossed, it would mean the force at that one single point is trying to go in two different directions at once, which, yeah, that's impossible. And finally, how close the lines are together tells you how strong the field is. And this brings us to that last rule, which is super visual. Wherever the field is really strong, we draw the lines all jammed together, really dense. And where the field gets weaker, we draw them nice and spread out. It's a simple and honestly brilliant way to see the field's strength at a glance. So once you know those rules, you can start mapping out all kinds of setups. For a single positive charge, you get these lines radiating straight out, kind of like the sun's rays. For two positive charges, you can literally see the lines pushing each other away. But check out that last one, a positive and a negative charge together. This beautiful pattern, it's really, really important. Yeah, that specific combination of a positive and a negative charge kept a little distance apart. It actually has a special name. It's called an electric dipole. And get this, it's one of the most important building blocks in like all of physics and chemistry. So, what is it? The definition's super simple. 2-point charges, same strength, but opposite signs. That's it. Sounds simple, right? But oh man, is it powerful. And trust me, these things are everywhere. The tech behind a TV antenna works because of them. And on a much deeper level, so many of the molecules that make up, well, everything, including us, act just like these tiny little dipoles. Okay, so that leads to a really cool question. We know what the field made by a dipole looks like. But what happens if you take a dipole and stick it inside another electric field? The short answer? The field grabs onto it and tries to twist it. It applies a rotational force, what physicists call a torque, and it tries to make the dipole line up. Let's walk through what's happening here, this little dipole dance. First, the external field gives the positive end a push and the negative end a pull in opposite directions. Now, because those forces aren't in the same spot, they create a twist, a torque, and that torque just keeps on rotating the dipole until, bam, it finally clicks into place, perfectly aligned with the field, kind of like a compass needle pointing north. Okay, remember way back at the beginning? That wild picture with all the grass seeds making that pattern? Is the light bulb going off yet? This is it. This is the big aha moment. Each one of those grass seeds is neutral, but the electric field is so strong that it shoves the charges inside the seed just a tiny bit, turning each and every seed into a temporary little dipole. And what do dipoles do in a field? They align. So that incredible pattern we saw, it's literally millions of tiny little grass seed dipoles all snapping to attention and pointing along the field lines, making the invisible completely visible.
So, this whole idea of dipoles lining up, it's not just some cool physics demo with grass seeds. No, it's way, way more important than that. In fact, it's fundamental to our very existence, and it's all thanks to one very, very special molecule.
And that's because of this molecule. Maybe the most important dipole in the entire universe, the water molecule, H2O. Now, the whole molecule is neutral, but because of that famous Mickey Mouse shape, the oxygen end is a little bit negative, and the two hydrogen ears are a little bit positive. It's a permanent, natural-born dipole. And this tiny bit of imbalance, this dipole nature, is what makes water a total superstar. On the left, you see stuff dissolved in water. On the right, you see exactly why. Those positive and negative ends of the water molecules act like billions of tiny magnets, grabbing onto other charged particles and pulling them into solution. This is exactly why you always hear water called the universal solvent. When you drop salt in water, the water molecules swarm the salt crystal. The positive hydrogen ends grab the negative chloride bits, and the negative oxygen ends grab the positive sodium bits, and they just pull the whole thing apart, piece by piece.
I mean, think about that. Without this one simple property, life as we know it just couldn't exist. This dissolving action, all driven by the dipole nature of water, is the foundation for pretty much every single chemical reaction happening inside your body right now. Which brings us to this incredible quote from the material we're looking at. I'm just gonna let that one sit there for a second. In a very real sense, your existence as a living being depends on electric dipoles, from invisible forces to the chemistry of life itself. Wow. Kind of makes you wonder, right? We've just peeled back the curtain on one invisible force. What other hidden forces, what other unseen rules are out there right now, quietly shaping the world we think we see every single day? Something to think about. Thanks for tuning in.